today mostly about constructible sets and locally closed sets. So maybe X, a generalized topological space. So the first property is proposition to prove is that the following are equivalent for a set A inside X. One is that well, exists F closed and U open such that A is the intersection Q in F. Second is that for some U open set, A is the intersection of U its A's closure, meaning that Q is open in its closure. And three is that Q is locally closed, meaning that for all A in A, we can find UA a neighborhood of A such that A intersection this neighborhood is the closure of the intersection this neighborhood.
A neighborhood, you mean open?
Open, yes.
Okay.
Open which contains A.
Yes.
Okay? Let us prove this. So 1 implies 2 is kind of easy. If A is the intersection of U with F, then F contains A. So if we intersect both sides with closure of A is the intersection of A with closure, which is this, which is this. So easy. 2 implies 3. Well, it's obvious, taking U to be, taking UA to be U. Okay? 3 implies 1. So, for any A, we have this UA, which is a neighborhood of it, such that A intersection this neighborhood, and A closure intersection this neighborhood. Move to this board. So let us take U be the union of those UAs, which is open, and the intersection of A with Q is the intersection with all the UAs. And this, we use the property of UA, and now we read backwards, replacing A with A bar, and get that this is exactly intersection U, which is, well, A bar is a closed set, so we got 1. Okay, any questions about this? Okay, so I wish to remind you the notion of constructible sets. So, definition, collection of constructible sets is the algebra generated by all open and closed sets claim C inside X is constructible if and only if it's the union of finitely many locally closed sets. Okay. Let's prove this fact. So a proof. We denote by A the algebra generated by these open and closed sets. So we have two inclusions. So first part, if I have C, which is the union of the I locally closed, then C a finite union. Thank you very much. Then it's in this algebra like that. Each Ci, by the theorem just had, is an intersection of a closed set with an open set. So it is certainly in the algebra, and we take a finite union, so it gets also something in the algebra. Okay? For the second direction, this board. So let's show that the finite unions of all locally closed sets is an algebra. Then, well, union to is such, this is clear, intersection of two. This is a little less clear, but if I take F intersection U1 closed, one locally closed set, and the intersection be a second locally closed set, you can rearrange this to make something closed, intersection something open. So if I now have intersection of finitely many of those, I can just rearrange stuff. 1, 2, M, Y, I, the union, 1 to M, turning 1 to M, the intersections. Okay? And for complements, let me use this as an exercise. That if a set is in there, then its complement is there. Easy. And I don't want to get into it. Okay. So I have another board here. Any questions for now? Good. So the third thing that they want to do is a proposition let A inside X be constructible, then there is a non-empty open dense subset of the closure. Okay, there are a few ways to prove this. I'll present one and then discuss the other. So, proof. We already know that A can be written as the finite union of locally closed sets. So let me do the following. Let me define Zi, that the I is a bad set, be the closure of EI minus EI. These are all bad sets in some sense. Let Z be the ultimate bad set. and let O be what's left. Then I claim that O lies inside A, O is open in the closure, and that O is dense in the closure. Okay. So 1, O is inside A. If I take Z and I look at its union with A, then I have the union of these sets with the union of these sets. So I get the union of these sets, which is the same as the closure of the union, because I have a finite one, which is the closure of A, because A is this union. So now let me remove from both sides the set Z, then A bar without Z, which is just our O, is inside this union minus A, in particular it's inside A. Okay? Second thing, ouch, is to show that on inside the closure it's open. That's also pretty clear, and the reason being that, well, we need to show that its complement in A bar, which is Z, is closed. It's enough to show that each Zi inside A bar is closed, and Z is their union, but the set epsilon I was locally closed, so it's open inside its closure. So if I take the complement, which is Zi, then it's closed here, and that this is of course contained as a closed set here. So Zi is closed inside closure of A. Okay, now for the a little bit tricky part is to show that O is dense in A. I want to leave this on the board, so I will erase this. So let us do the following. Suppose O is not dense in A bar. There is some open set V which interrupts it being dense, meaning that V lies in A bar without O, which is exactly the union of all Zi's. Let us now take I0 be the minimal index such that there exists U non-empty open, which lies inside the union of the first I naught, Zi's. This is a sublemma, subclaim, that I naught is at least 1, and that this set U is not contained in the last one. Why, in general, U is not contained in any Zi. So why does this apply here? Because for this we just plug I equals I naught, and for this we plug I equals 1. This is because Zi was exactly the boundary of epsilon I, which cannot contain anything. This is dense in this. So what we
So,
have.
sorry, you have two statements in the subclaim, right? I know this is bigger.
It's bigger than 1, and
okay.
U is not here.
You're explaining which one?
I'm explaining both. I say that if for any I, this is true, then both of these are true. This is just plugging I equals I naught. And for this, I go to the definition of I naught and plug I naught or I equals to 1.
Okay.
Okay, so U cannot be in the first one.
So you have to show that U is not contained in the ZI.
Yes.
Okay.
And how do I show this? Zi is exactly something minus, sorry, the closure of something minus that thing, which cannot contain any open set, but because by the definition, this is dense than this. Okay? So I show this. Is it fine? Okay. So we now can take U and drop the last Zi outside. Then this is something which is open because U is open, Zi is closed, and it's not empty because U is not contained in this last one. This is not contained in the union on one less Zi, contradicting the minimality of I know. So O is dense in closure of A. Any questions up to now? Okay. So there are other ways to show this, and I want to discuss one because it will be helpful in a couple of seconds. So another option which was suggested by Uri in class is given A, let us define U of A, which is the set of all points at which A is locally compact. Because this UA neighborhood of A such that in this neighborhood I have this. What one shows is that U of A is U of A. This is an exercise for you. Second thing one shows is that A is U of A if and only if A is locally compact, locally closed, sorry, which you have already shown it in one of these, in what was written here a few minutes ago. And the third thing that one needs to show in order to complete this is that A is constructible. From these two it follows that U of A is always locally closed. And now if we're given a constructible set, I can look at this process. A1 is what's left after reducing U of A. A2 is what's left after reducing U of A1. So on and so on. Then I claim that my set is constructible if and only if, at some stage, this stops. So the easier direction is to show this, because then I can present A just as U of A union U of A1 union N-1, which is a finite union of locally closed sets. And the second direction is left as an exercise. This is in some sense a canonical decomposition of your constructible set into locally closed sets. And well, you can use it pretty easily to get an open dense set inside an open subset of A, a subset of A which is open and dense in the closure. Let's take the first one. What?
Take UA.
Take UA, just that.
Just that much?
So in particular, what I wanted to do when stating this is that, in particular, if A is constructible, then the set U of A is non-M. Because if it is, then A1 is A, and then A2 is A1, etc., etc., etc. And this process never finishes unless A is non-empty, but maybe I should have written this, but not today. Okay. So what we really want to do is to discuss the constructive actions. Okay, so let me really find this. A continuous action of a group G in topological space X is constructible if this map taking G and X to map Gx is constructible. And well, we'll see probably tomorrow, or I hope at least, that algebraic actions have this property. Okay? So what I want to do to make is that the following proposition: if I have a constructible action, not only that the orbits are constructible, they're actually locally closed. Okay, so let's explain why. So one needs to show first that the orbits are constructible, and then we'll prove it. So why are the orbits constructible? So take some x and x, and we want to look at the orbit of x. So I look at this map. When I take G cross this point x, it's of course closed in here. So the image by assumption is constructible. And the image is exactly on the first coordinate I get x, and the second coordinate, and on the second coordinate I get the orbit of x. So, well, if it's constructible, then it's the union of locally closed sets, and because I'm on this line whose first coordinate is x, I must be of this form. These are locally closed. So, they're the intersection. These are locally closed sets in the big space, and now I'm saying why they're locally closed in small spaces is nearly trivial. But this is the intersection of a closed set with an open set, and if I intersect both sets with this space, then I get that by definition this is a closed set. This is a locally closed set in this space. This is actually locally closed in x times x. And if I project on the second coordinate, I get a homeomorphism. So of course, I still get, because this is a homeomorphism, the orbit of x is the union of these AIs, which are locally closed. Meaning that the orbit of x is constructible. So,
Can you just say that the projection of one factor is open enough?
yes, but you still need to worry about, you have an open part and a closed part. And the closed part might get ruined. I mean, think about,
Oh, okay.
yes, just example, when you're projecting this component. Okay? But this is mostly technical. And And now, why are the orbits actually locally closed? Basically, because we can look at the sets of points at which they are locally closed. So, look at this set. Then it's non-empty, because what's inside is constructible. And it is G-invariant, because this is defined in manners of open and closed sets, and these are invariant with respect to the action of G. So we have an open, sorry, not an open, a G-invariant closed set which is contained in some orbit. It must be equal to the orbit. Okay? So in particular, we get
Excuse me, what are you arguing about?
Excuse me?
What are you proving at the moment?
I have shown that this orbit is constructible. I want to show that it's locally closed. Okay? So look at the set of points at which it is locally closed. This is a G-invariant set, which is non-empty, and it is contained in the orbit. So it must be equal to all of the orbits.
Yeah. Once more.
Okay. Consider this set, okay? We know it's not empty because what's inside is constructible. This is G-invariant because these are sets of points at which the set looks like its closure if you want to intersect with an open set. And all of these, this is something which is invariant under the action of G. So this is an invariant set under G. Okay? So you have a G-invariant subset inside a G-transitive space. The only way for this, which is non-empty. The only way for this to work is if it's equal to the entire space. But then Gx is locally closed. Okay, any questions? Remarks?
So tell me if you did it at the beginning, but could you provide an example of something which is constructible but not locally closed?
If you take maybe something like this, take something like this, then near this point, well, it is constructible because it's the union of what's inside and this R. And if you look at this boundary, this point, sorry, then you don't look locally like a closed set. Okay? This is an example of a constructible set that is not locally closed. And there are more examples. Okay, if there are no more questions, then I want to do something else. Second, please. So I want to maybe go back to last tutorial and do something that I didn't have to do. Sure.
As far as I can see, I don't think this was investigated much, but obviously one in the definition of the use sequence, one see an obvious notion of dimension, and I don't think this was investigated in any sense. Somehow your picture there is the two-dimensional.
Yes. So
the constructibility of it is two-dimensional nature, and okay, I'm saying that this is one can study this further, and no one ever did as far as I know.
exercise. Okay, but this is a good remark indeed. So if there are no complications, and, I want to move to something else. So, any more questions, remarks? Speak now or hold your tongue forever. You of course can ask later, but okay. So this is theorem. let V decide an n-dimensional fine space, a variety. Then V can be written as a finite union of irreducible varieties. So, as for proof, well, we had this correspondence last time between prime ideals and irreducible varieties, and between general varieties and radical ideals. So basically what one needs to show is that this is the same as a radical ideal J inside polynomials in n variables is the intersection.
Did you define irreducible?
Yeah, sure, just a minute. Is the intersection of many prime ideals. Yes. An irreducible variety over here is a variety that whenever you can write it as a finite union of closed subsets, Zariski closed subsets, one of them is everything. So for example, if you look at the variety, this variety, which suits to the zeros of fy equals to 0, it's not irreducible, because you can look at this part and this part. I hope you saw when it turned like that. For example, and there are more examples, of course. And we saw last time, it was in the five last minutes, or maybe it was a bit rushed, that if you, well, Nullstellensatz gives you that your variety is always the vanishing point of some radical ideal, and that your variety is irreducible if and only if this ideal is prime. Okay, so this is the nature of this correspondence here. Thanks.
May I make a note? It may appear that this is a theorem in algebra, but actually, whenever you have a theorem in topological space, then every closed subset is a finite union of irreducible points.
But, well, at least for now we're working in the neighborhood of algebra, so I wanted to present it in this case, but this is a true remark and it is useful sometimes. Thanks. So, this is this first step. So a second step is an exercise for you. It's not too hard, and maybe you'll solve it first time in the end. Is that let J be a radical ideal in a general ring, maybe with unity and commutative is needed, but nothing more. That if I have two elements in my original ring whose product is in J, then J can be written as the radical of this ideal intersection the radical of this ideal. So maybe you can see for yourself that I'm going to use in some sense some induction. Noetherian argument is Noetherian is a better word in this context. I'm just starting to go up. So now let's take a general radical ideal in the ring of polynomials, J. Take J radical ideal in space. So if it's not prime, then we can find A and B which are not in J, whose product is in J. So by this manner, we represent J as the intersection of two larger radical ideals. We can now do the same for J1 and J2 if they are not prime. And this must halt at some point because of Noetherianity. So if I order them, I don't know, in this manner, and go on, then I have to have color. I don't, but okay. Exactly. Or you can just do it like this. You can take this, these, just unite larger and larger sets, and because something needs to be stabilized at the end, this process must halt at some point. Okay? If you have your bar.
I think that the general statement, I mean, you put in special case, so the very general and very, very easy statement. Whenever you have, again, in a very topological space, then every set is a finite unit of irreducible ones, and assume you have a closed set. Oh, sorry, assume you.
At the end, you have to prove that this topology is Noetherian. To do this, you have to use feedback basis sets.
Which
is this thing?
Yes, basically.
Sequence of ideas that way. Right? So you have to prove that this topology is Noetherian, right?
yes.
And that's the proof.
I'm sorry.
Let me just finish this.
Okay, sure.
Assume you have a set, a closed set which is not irreducible. Sorry, which is not a unit of irreducible ones. Let's say that nice sets, nice closed sets are finite unit of irreducible ones. Assume you have a set which is not
nice.
Then you have a minimal one which is not nice. And this minimal which is not nice obviously is not irreducible. Otherwise it was nice. So it's a unit of two. But each in these two is a finite unit of irreducible ones, and your original one. And hence this union of these two pieces, which each is a finite unit of irreducible ones, is a finite unit of irreducible ones, and you're done. I mean, yes,
Okay, this is.
you need the Noetherianity of these spaces to be established.
Well, we know this, and well, I'm not sure if this is actually easier, because but I'm still sorry. So well, I think that I'll finish for today if it's fine by you.
I think it's just completely on the nose equivalent. It's Noetherianity
Yes.
and the fact that it's every set is a set of irreducible ones. And so
I think yes, it should be. Sounds logical. Yes.
it's just different perspective of what is from what.
So, class dismissed.